So in this unit, we're going to shift our focus and we're going to be focusing on gases. Now, before I get into quantitative ways of measuring gases and characteristics of gases, I need to talk about the kinetic molecular theory. Now, there are 4 main points of the kinetic molecular theory, and these points are the foundation for all of the assumptions we're going to be making in this unit. So the first is that when you have a gas, it is simply a collection of particles and they are constantly moving. So those molecules or those atoms, those particles are always in motion. Another assumption that we make is that those particles that are moving, those gas particles, are not attracted to each other and they don't repel each other. So when they bounce off one another, they simply bounce off, they don't stick to one another and they don't repel one another. That's going to be really important when we talk about the ideal gas law at the end of this unit. Okay? But that's an assumption that we're making with all of the different gas laws we're going to be using in this unit. The third is that there is a lot of space between the particles. So the particles themselves don't take up a lot of space. Instead, it's mostly empty space that a gas is made up of. So you have the particles floating around in constant motion, but they're so distantly spaced out that the majority of the space that that gas takes up is actually just empty space. And then finally, the speed at which those molecules, those gas molecules, move is a result of temperature. So if you increase the temperature of a gas, those particles are going to move faster. If you decrease the temperature of the gas, then the particles are going to move more slowly. And that's going to affect a number of different characteristics of gases, as we will see when we get to our gas laws. But what we're going to be focusing on today, the first quantitative characteristic of gases that we need to focus on is pressure. Now, pressure, this chemistry definition of pressure is that it is a force exerted over an area. Okay, so the quantitative way of representing this is that pressure is a force over a given area. So why does this matter, and how have we experienced this already in our everyday lives? Think about when you've been stepped on before. Which would you rather have? Someone who's stepping on you with a shoe, like a tennis shoe, or someone with a stiletto? Now, that person can weigh the same amount. The force can be the same. The difference is what they're stepping on you with. So a tennis shoe has a large surface area. So if you have a large surface area, the number in your denominator will be large, causing the pressure then, when you divide by a large number, to be smaller. So it doesn't hurt that badly. But if someone steps on you, that same person steps on you with a stiletto heel, the area that that force is being imparted over is much smaller, causing the pressure that you experience and the pain you experience to be much larger. Okay? So that's pressure. Let's talk about pressure for us. So we know when we say, oh, we went up to the mountains. Well, there's lower atmospheric pressure. What exactly are we talking about? Well, if you think about the atmosphere, the air that makes it up, what is pushing down on you is a mixture of oxygen, 21% of the air, nitrogen, which is 78% of the air, and other gases. Now, those gases are pushing down on you, and so it makes sense that if you were up high on a mountain, there's going to be less gas pushing down on you than if you were at sea level. And if you went below sea level, then the pressure would be even higher. So at sea level, approximately, the pressure tends to be about 1 atmosphere. If you go way above sea level, because there's less gas pushing down on you, the pressure is going to be less. While if you're below sea level, there's even more gas pushing down on you, so the atmospheric pressure would be larger than 1.0. So notice I introduced one unit already of pressure, atmospheres. Okay? Let's look at a couple other units that we could use. All right, so units of pressure. The first that we already looked at is atmosphere. So when I'm at sea level, I have a pressure of 1 atmosphere. Another unit of pressure is millimeters of mercury, and I'll talk about that in just 1 second. So 760 millimeters of mercury is 1 atmosphere. Okay. Also, one last unit that we'll look at, and there are a number of ones that you will see, but I'm just going to give you the most common ones we use in chemistry. Kilopascals. Okay? I can say 1 atmosphere is 760 millimeters of mercury. I can say 1 atmosphere is 101.3 kilopascals. All of these are equal to each other. All right, where did millimeters of mercury come from? Well, what they did is they took this tube, it's a one-sided tube called a barometer, and they filled it with mercury all the way up to the top. Then they flipped it, they inverted it, and put it into a bath of mercury. And what happens is atmospheric pressure will push down on that bath of mercury, causing the mercury to rise to a certain level, okay? And so the higher the atmospheric pressure, the higher the mercury will rise. Well, at sea level, the mercury will rise to exactly 760 millimeters of mercury. And so that's where we got that unit. I just think that's really cool that that's one unit that we have, simply based on how high mercury rises, based on what pressure is exerted on the bath of mercury. Okay, so now we've seen 3 units of pressure. Let's do a couple of conversions to make sure we're comfortable with those conversions. So for example 1, it tells me I have 1,277 millimeters of mercury. Okay, and it's asking me to convert this into atmospheres. So I'm going to put millimeters of mercury on bottom, and I'm going to put atmospheres up top. Okay, and based on what I just shared with you, 1 atmosphere is 760 millimeters of mercury. And so what I'm going to do is I'm going to take 1,277 and I'm going to divide by 760, and unrounded I get 1.6803. Okay, keep in mind 1,277 has 1, 2, 3, 4 sig figs. This is an exact relationship, so I cannot use this in determining significant figures. And so I want 4 sig figs, 1, 2, 3, 4. So this is going to be 1.680, and my units are atmospheres. Okay. Let's look at the next example. 11.5 kilopascals, and I'm being asked to convert that into millimeters of mercury. So I'm going to put my units of kilopascals on the bottom. I'm trying to get into millimeters of mercury, so I can do that directly because all of these, the conversion factors I gave you, are equal to each other. I know that 760 millimeters of mercury is equal to 101.3 kilopascals. Okay, so I'm going to take 11.5, I'm going to multiply by 760, and then I'm going to divide by 101.3, and the value that I get, unrounded, is 86.278. Keep in mind, I want 1, 2, 3 sig figs, 1, 2, 3. So this is going to round to 86.3, and my units are millimeters of mercury. Okay. Finally, 0.558 atmospheres. I'm going to put atmospheres on bottom, and I'm going to put kilopascals up top. Okay, let's look at this relationship. So I know 101.3 kilopascals equals 1 atmosphere. And so what I'm going to do is I'm going to take 0.558, and I'm going to multiply by 101.3. And unrounded, I get 56.525. Okay, I need 1, 2, 3 sig figs, 1, 2, 3. So 56.5 kilopascals.